Yeah.
Howdy, we're the Aerospace Engineering. We're going to introduce the team before we present. So I'm Trevor Burke from Dallas, Texas.
Hi, I'm Lisa Alexander from Houston, Texas.
I'm Braxton Hornbuckle from McAllen, Texas.
I'm Jaden Wood from Marietta, California. I'm Lauren Rodriguez, also from McAllen, Texas.
I'm Sarah Smith from Des Moines, Iowa.
I'm Raju Carlos Goody from Overland Park, Kansas, and this is the Lunar Orbiting Volatile Experiment Satellite, aka LUVSAT.
All right, so our mission was to design a concept of systems for a 6-unit CubeSat to orbit the moon and measure and map volatiles on the moon. A CubeSat is a small 10-centimeter cube of a satellite. This is a full-scale model of such a cube. For our satellite, our LUVSAT, we got 6 of these CubeSats that were all interconnected to form one larger satellite. Right here is a full-scale mock-up of the CubeSat with the solar panels deployed. And so we don't have a lot of space with our CubeSat to measure volatiles. And the volatiles we're measuring is any sort of gas with a very low boiling point. And so it's practically a gas on the moon. And so we had to have a number of concept designs in order to make our satellite be able to accurately map the volatiles on the moon.
So before our group began designing our CubeSat, NASA Ames provided us with a number of constraints. These requirements guided our research as we explored different ways to map the lunar surface. For example, one of these requirements was that the total power of our payload was 10 watts. The requirements also restricted the size of our payload to 4 units of our total 6-unit CubeSat, with a mass of no more than 5 kilograms. Again, the goal of our mission is to confirm the presence, map the concentration, and plot the density of a wide array of volatiles on the lunar south pole.
Now, our cube satellite is based off of several driving assumptions. First and foremost, our CubeSat, LUVSAT, is based off of NASA Ames BioSentinel. So we are resting on the assumption that BioSentinel meets the specifications for a 6U CubeSat. We are also assuming that NASA Ames has provided us with 2 gigabytes of storage. We are assuming that our lunar orbit will be stable for about 15 days, which is just enough for our nominal mission. And finally, we are assuming that we will have access to a 12-meter satellite dish for at least 1 hour a day. So throughout the project, me and Jaden made extensive use of CAD software, specifically Autodesk Inventor. With our CAD model up here, we were able to visualize the geometry of our CubeSat and, more importantly, using the mid-to-array renderer, see how light reflects and bounces off the solar panels. Right here, you can see our CAD model in its completed state.
As Trevor previously mentioned, our satellite is composed of 6 10-centimeter unit cubes, and 4 of those units are allotted for our instruments, the 2 instruments that we chose, which will sense the lunar volatiles. So the 30 by 10 by 20 centimeter body of LoveSat holds the 2 instruments in the front 4 units of our satellite, while the back 2 units are allotted for the rest of the systems that NASA Ames is providing us. The structure of the 6-unit body is made of aluminum, as well as the panels on the outside that shield the structure of our satellite. The 4 solar panels are mounted on the front of our body of the LoveSat so that the solar panels will constantly face the sun to power the satellite for our mission. Now Braxton will discuss the internal and external features of our satellite.
So right here on this CAD model, you can see on the exploded view of that square right there, that would be Birch's. That is our IR spectrometer. And next to it is our chameleon imager, which is our camera. You can see on the top panel right there, which will be facing towards the moon, it has been machined through and designed so that these instruments can face outward. Also, we have a medium gain antenna, which has been modified by Lauren and Raju, which is broadcasting on X-band. This antenna is also directable in 3 dimensions so that we can always keep in contact as much as possible with mission control, as well as transmit and receive data.
For our mission, we selected the lunar South Pole as our region of observation. We know already that volatiles are present here. So now our task is just to identify which ones are specifically present, pinpoint their exact locations, and report the density of these materials. The region we will be observing is 1,250 kilometers in diameter, and it receives no sunlight. For us, this is a good sign because it means we have shadowed craters that are full of ice, cold traps that have hydrogen volatiles, and even fossil records of our early solar system. We did consider collecting data at both the north and south poles of the lunar surface. However, previous sensing missions and data that we do know lets us know that the South Pole has a lot more potential for volatile exploration than is the North. So rather than sensing twice per orbit, we're going to save our battery and maximize data collection at just the South Pole. So to do this, and to allow for constant communication with Earth and recharge our power systems, we have a slightly elliptical orbit selected. Its period is about 164 minutes per orbit. At the paraloon, we will be collecting our data. The paraloon is, in this case, the South Pole. We'll be traveling at this point at 1.78 kilometers per second, and we will be at an altitude of 100 kilometers. We will be sensing for a total of 11.7 minutes, which takes just 7% of our orbit. So for the remaining 152 minutes of our orbit, our CubeSat will be moving a little bit slower so that we have time to recharge our battery systems using solar panels and transmit our data back to Earth safely. At the apoloon, our LoveSat will be traveling at its slowest point at 1.2 kilometers per second, and will be at 1,000 kilometers in altitude. So as you see that little chart right there, it's a lot closer at the bottom at the paraloon than it is at the top. So it goes faster at the bottom, and that helps us conserve energy because we're only sensing for as long as we need to before slowing it back down to transmit everything back to Earth. So looking at our mission as a whole, we have 4 phases in our mission. First, we have launch. NASA Ames will be planning and launching our satellite for us. So we are going to just assume that we will be placed into the orbit that I just discussed, and that it will be in a stable state so that we don't have to worry about immediate realignment or orientation shifts. Nothing will be powered on until we get to the initialization phase. Here, we will turn on the power of all of our systems, we will be deploying our solar arrays, and we will be making sure that all our systems are functional and that we have signal back to Earth. Next is our 10 days of planned operation. This is most easily divided into the 2 sections I just discussed of data collection and transmission and recharge. We estimate that we will get 100 orbits out of our CubeSat in these 10 days, which totals to about 19.5 hours of data collection.
Beyond this point, we will be doing nothing to decommission our satellite from its orbit or from its functionalities because there is a chance that it continues to function. In this chance, we'll be placing our CubeSat in an alternate concept of operations in which it will be collecting data at every South Pole pass, and it will only be downloading the data back to Earth when the antenna and the receiver side align. Eventually, when systems inevitably do fail, our CubeSat will either crash into the moon itself or experience orbital decay and become space debris. Given the very, very small size of our CubeSat, either of these options is acceptable. Ultimately, so long as we receive 10 functional days of data, we have a successful mission.
So after looking at the orbit, what we have to consider is the orientation of the satellite in this orbit. Now, the main considerations you have to make for this is where the solar panels are facing and how the instruments are also pointed. In consideration to the solar panels, we had to discover the optimal orientation for energy production. Now, we found that this was when the panels were faced perpendicular to the Earth-Sun line, essentially meaning we're facing the sun the entire time. This is because the LoveSat recharge period is essential for the instrument's sensing abilities, and that means that we're able to get that's because we have to get the optimal exposure and thus get the most efficient data collection from our power. This is also the reason why we chose the full moon phase for our mission, because we're able to get that full exposure. Now, to maintain this satellite orientation, LoveSat will move 1 degree per day in order to stay perpendicular to that Earth-Sun line and still continue to face the sun throughout the mission. The other consideration we made was how the instruments were facing during the orbit. Where they face as LoveSat, we had to think about where they face as LoveSat orbits the South Pole, and so we had to think about how efficiently we wanted to collect this data in consideration to where the aperture and lens of Birch's and the Chameleon Imager, our instruments, were facing. They'll be oriented parallel to the surface of the lunar South Pole, and in order to save energy, that's never going to change. So essentially, it'll be facing up the whole time, or parallel to the South Pole. This also means that the 10 by 30 centimeter side is what's going to be facing that surface. This is achieved with the attitude determination controls given to us by NASA Ames in their 2U segment of the satellite, and that allows our instruments to do their jobs. And then after looking at the bigger picture, what we have to look at is the design constraints and the specifications we were given at the beginning of the project. Now, the main 3 constraints we were given were mass, power, and volume. 6 units, what we discovered, is a small amount of space, especially when 2 units is already taken up by NASA Ames. For our payload segment, we were given 5 kilograms of mass, 10 watts of power, and 4 units of volume to work with. The table shows you how we allocated our resources, and Raju will later discuss how we achieved those 10 extra watts of power that you see on there. Most of the telling information that you see up there is in the margin. For a typical mission, what you want to do is use about 60% of your allotted power in order to avoid battery decay, and the good thing is that we managed to use only 53%, but as you can see, volume ended up being the most limiting factor that we were working with, which led to a lot of trial and error with what instruments we chose to use.
NASA Ames is providing the Biosentinel bus to aid our design for volatile sensing. Ames has all the systems that we need to run our instruments for our mission. Starting with the most important system on the bus, the power system, it has solar panels to recharge the battery cells. The power system must provide wattage to run all the instruments and all the systems on the satellite for the duration of our mission. The orientation of our satellite is very important for remote sensing, solar power, and communication. The attitude control system orients LoveSat using a star tracker, reaction wheels, and an IMU, which is an inertial measurement unit. The star tracker measures the position of the stars to determine where we are in space. The reaction wheels enable a precise pointing of the satellite with 4 wheels that will slowly rotate the spacecraft to orient it correctly. And lastly, the IMU, the inertial measurement unit, will measure linear and angular motion for configuration during our sensing period. Now, the communication system between LoveSat and mission control is achieved with an EPS, an electric power system, an iris transponder, a medium gain antenna, and 2 low gain antennas. The The EPS, the electric power system, contains a computer and memory storage for data collection, while the iris transponder receives and transmits signals. The medium gain antenna is our main system for transmitting data, while the two low gain antennas are only intended for transmission if the medium gain antenna fails to operate. The propulsion system on board the satellite uses cold gas thrusters to orient the medium gain to face the Earth to maintain communication. And lastly, the thermal system that Ames is providing us maintains a working environment between 10 degrees Celsius and 50 degrees Celsius. For the selection of our instruments, it involves a balance between multiple factors, specifically mass, cost, reliability, and power consumption. For remote sensing, there are active and passive sensors, in which active sensors use more power than passive sensors. Active sensors require an external source of power to sense the data, while passive sensors simply just detect the input from the surrounding environments. With the limited power that we have, passive sensors met our constraints. And now Trevor will talk about the instruments that we chose.
All right, so the most critical thing for our sensors is it had to be able to measure the volatiles. The main volatiles that we're measuring was water. Previous studies on the moon had detected that there is water on the moon. However, where it is and how much it is has not been fully determined, because the most studies that have been done using iris spectrometers only tell elemental form of hydrogen, which leaves it ambiguous to whether it's really water or another compound of hydrogen. And so, for that reason, we chose birches and chameleon in order to measure the water and water-like molecules on the lunar surface itself. With this, we can create an accurate model and understand the thermodynamic history of the moon in a much better way.
So the primary instrument on our CubeSat is birches, or the broadband infrared compact high-resolution exploration spectrometer. Birches is essentially a scaled-down version of OVERS on the OSIRIS-REx, which some of you may recognize as part of the New Horizons mission. Birches, as the name implies, is an infrared spectrometer and can see down to 1 to 4 microns and has a resolution of 10 nanometers. With this, we can distinguish volatiles from our altitude of 100 kilometers. The volatiles that we'll be able to sense with birches will be water, hydrogen sulfide, ammonia, carbon dioxide, methane, hydrogen, hydroxide rather, and mineral bands such as silicates and oxalates. We believe with birches sensing these volatiles, we'll be able to support future ventures into space. After all, these volatiles will be able to aid said future ventures in everything from creating rocket fuel on site at a lunar base to creating water or even lunar air. Birches has a 4-sided iris, which will allow it to maintain a spot size and a 0.6 to 6 degrees field of view, which will allow it to maintain a sufficient footprint over the moon. We chose birches for our CubeSat because it was specially designed for CubeSats, taking up only 1.5 units, weighing 2 kilograms, and taking up 5 watts of our allotted 10 watts of power.
In order to get really, really accurate and precise data from birches, we had to prevent any interference from the heat of the molecules on the surface that would generate extra current or dark current. In order to do this, we had to cool the whole plate in the detector down to really, really cold temperatures. The BioSentinel satellite can cool the temperature to about the average temperature of a human, or 30 degrees or 300 degrees Kelvin-ish. And so our instrument had an extra cryocooler system that can cool it down to about 110 degrees Kelvin, which is over negative 150 degrees Celsius. Bird.
In addition to birches, we added the chameleon imager as a secondary instrument on our payload. This instrument benefits our mission because it captures high-quality, multispectral images from the height of our proposed lunar orbit. Chameleon, when used in conjunction with birches, will provide us with a visual, allow us to distinguish a location, and ultimately help us map various volatiles on the lunar surface. The camera has a mass of 1.35 kilograms, consumes less than 3.5 watts, and takes up a total of 2 units on our 6-unit CubeSat. Moreover, the camera comes with an additional 126 gigabytes of data storage solely for its images. Overall, its compact size and low power consumption makes it an ideal candidate for a CubeSat mission.
All right, so after we finish this data back to our receivers on Earth. So as of now, in the AIM 5